Well, good morning once again, and welcome back to this course on environmental bioethics within the program of uh, bioethics in Tamaulipas. And today we have the topic of succession and population growth, and then what is known as a climax community. First, looking at it in nature, and then applying it to the human population growth and population density. Okay? Because we happen to be one of the 2 million species on Earth, and we take up some space to live physically. That's called the footprint, and that has an impact on the environment. But to kind of get to the punchline here from the very beginning is we actually have to live somewhere, right? We have a right to live somewhere, and that's going to take up some space. So we'll look at these factors. But first, I want you to understand what is known as succession in nature to come up eventually to what is known as a climax community. We're going to look at the different stages of succession, starting from the pioneer.
Yes, hold on.
Then the intermediate species, and then finally the dominant species of a climax community. So broadly, it's kind of 3 steps: the beginning, the middle, and the end. Right? Natural succession. In human population, we'll see how that applies, and we'll look at the concept of a carrying capacity. What is this carrying capacity that applies to all species on Earth? Also look at the growth curve. Actually, this should go before carrying capacity. Just switch the order of these two here. All right, so we start with growth curve, and capacity environment, and finally we want to look at global developmental goals for the human population. Okay, so I'm going to move forward. I forgot to ask if you had any questions or comments from previous lectures. No? All right. So let's look at what is this succession in nature.
Okay, there's nothing I can do. I'm busy.
It means that there is going to be replacement of the population of species from time to time. There's going to be some natural replacement. Remember, the key issue here is the concept of population, right? And what is the population speaking about nature? What is a population? That word is loaded, it's very significant and very important. What is a population is the question. Any number of individuals of the same species, what? You have to ground it, what? Flying around or in open space? In a particular area, in a specific area, right? So once you put a number of individuals, any number of individuals in a specific area, then those individuals are going to be impacted by the area where they live, right? So you have the biotic factors, which are what? What are the biotic factors? The number of individuals, the living factors, right? Biotic, right? Okay, I need you to come up to speed Saturday morning. Okay, so biotic factors are the living organisms. We're talking about a population, so we're talking about how many species? Yes, how many species in a population? A population. One species, right? Number of individuals of one species in a particular area. So the biotic factors is the number of individuals, those individuals of that species. For example, in this room, all right, we have a population of how many individuals? 3. And we are the same species. So it's just a very simple example. It's so, it's intuitive. So I'm trying to emphasize the aspect of population on the ground, the population on Earth, realistically as we live. And then the abiotic factors, and non-biotic factors is going to be what? Exactly, the actual place, the conditions, the climatological conditions where the population is existing, right? So for us here at this time is the room, the space in the room, the temperature in the room, the humidity, the lighting in the room, all those physical conditions, right? All right. So in nature, we have any number of populations interacting with each other. And so it's a dynamic state. It's a dynamic state, right? When we look out the window into nature, it looks like everything is kind of stand still there, but not really. There is a dynamic state going on of individuals coming in and out of a population, of populations coming in and out of a community, right? And so on and so forth, depending on what region we're talking about, how small, how large. And we can go as small as you want, right? Like microscopically, the tip of a pin, which I'll show you in a minute, or we can go as large as we want, which could cover several hundred square kilometers of range. Range would be the area that a species needs to live, that a population needs for, to live stably, all right? It's called the range. So what will happen is that there are stages of succession that happen in nature. When an area is going to be colonized, when an area of the earth, or this applies also to the oceans, to the land, and to the water environments, okay? This area is going to be populated. Let's say that we're going to populate the earth with species, with living species. There are basically three stages, broadly speaking. The first stage is known as a pioneer stage, when these species are colonizing an area. They're beginning to colonize an area, okay? So these are key terms: pioneer species, colonization, right? It's the first stage. Then the second stage are called intermediate stages of succession. These are precisely the stages of succession occur in between, until finally that area, that community, will become what is known as a climax community with some dominant species in the area. Let's look at it in more detail, because that's the big picture: pioneer species, intermediate stages, and climax community. Okay, Louis?
Well, each stage leads to the other stage.
Yes, there is a progression here. There's a progression here, all right? As long as the climate stays stable, more or less stable, even with seasonal changes throughout the year, but the climate stays more or less stable, then there will be a progression here toward greater and greater abundancy and greater biodiversity. It's just kind of built into nature, that nature will populate an area, will colonize an area, and will thrive in that area, as long as the climatological conditions stay more or less stable. All right? Now, I'm saying a lot in a little time. It'll be more clear as we go through an actual example. So let's go through an example. And let's concentrate on the plant species for now, right? Because you understand that in an area that is originally barren, let's say just rocks, the first things to colonize there typically will be plants, and then the animals will follow, because you need producers first, and then the consumers will be following those producers, beginning with the first layer of consumers, which are going to be what? The first layer of consumers are the herbivores, the plant eaters, herbivores, okay? Okay, I need you to be thinking ecologically and what happens in nature itself as we observe it. All right, so the first stage then is as pioneer species come in, okay? And typically there are lichens and mosses, lichens and mosses. Lichens in particular are very interesting because they are a combination, it's known as a symbiotic combination of fungi and algae. So what happens with lichens is that, say here's an example of a lichen growing on a rock. Okay. These lichens are fungi that absorb algae that grow within them. And so you have two different types of populations. Actually, you have they have the fungal population and the algal population, and they produce. So the algae, being a producer, being a photosynthetic organism, will produce food, glucose, for the lichen, and the lichen will then feed on that glucose, and itself, excuse me, the lichen produces acids as a byproduct of their metabolism. And what happens, what do you think happens to the rock? Most rocks are on the basic side. In other words, they're minerals, typically they're basic or alkaline. When you pour acid on a rock, what do you think happens? It starts dissolving. It starts dissolving, okay? So little by little, lichens dissolve rock into minerals that go into the soil. So they are enriching the soil with minerals. It's a long process, okay? And it's another type of erosion, but this erosion is done by living organisms as opposed to wind or rain or ice, like we saw in the water cycle. Okay, so lichens over a long period of time break down rock into minerals that go into the soil and enrich the soil, for then other plants to start coming in and colonizing because they now have some minerals to grow on. And that is the case then of mosses, right? So mosses also have the ability to come into an area that is fairly barren and start colonizing it too, because they need very little nutrition, and they are small and can survive. Here you have an example. You see again rock that is being colonized by mosses. I'm not sure that this is the ocean. That could be algae instead of mosses. But here, definitely, see mosses growing on rocks, all right? In the microenvironment, they'll find a little bit of nutrition there to grow, and they continue that erosion process. So the two large groups of colonizers of pioneer species are typically lichens and mosses. They're small, and they can get wedged into rocks and crevices and so forth and start eroding that rock over a long period of time into soil, into minerals that will go into the soil, right? Also, as they die, these individual patches of moss and lichens, and they have a lifespan, right? Every organism on Earth has a lifespan. Over that time they die, then they decompose by bacteria, which the other, you're right, the other colonizers here are microscopic, we don't see, but bacteria and fungi, which remember are saprophytes, in other words, they break down that organic material and continue to add to the soil, enriching the soil. So it's a natural progression here as plants and later animals come into an area, a barren area, to start colonizing it. Over a period of time, they are adding to the richness of that soil. They are enriching that soil. As the soil becomes more and more rich with detritus and decaying organic material, then other species can come in, which are a little larger and need more, they need more nutrition, which are typically grasses, shrubs, and bushes, okay? And these are the intermediate species, the intermediate populations that will come into an area and continue the succession, one succession after another. So here, for example, you can see that there is a variety of different shrubs and tall grasses and bushes, right? Each one of these, you can see, for example, these have a little purplish flowers sticking out, right? These would be shrubs, and they belong to one particular species. Just intuitively, they have these light purple flowers. So that's one population. This patch here is a population of whatever shrub this is, right? This is another one here. See, this little shrub has more of a grayish color to it, all right? And this one looks similar. So these other individuals would form a population of this other type of shrub. Here is a taller bush that is a little more woody, has some little stems to it. So this is another species, right? That forms a patch here. So that's a small population of whatever bush this is. Maybe these are some grasses down here, etc. So you see there are several different populations, right, of bushes and shrubs interacting with each other. And so they form what? They form a community, right? Remember, populations of different species coming together, they form a community. And typically, that's how it is in nature. You know, these natural communities, when we add the non-biotic factors, the abiotic factors like temperature and water and so forth, then that becomes an ecosystem, right? Becomes an ecosystem, which is more realistic because we don't have communities just living in space, but rather they are grounded on a particular place, which has its own climatological conditions specifically, right? There's no place on Earth that has no climate, right? Okay, so just mentally trying to make the scenario as realistic as possible. Mm-hmm. All right, so you see then there can be several stages of succession over the years. And first of all, there are several different cycles. The first cycle is a natural cycle that is going to happen, let's say, on a yearly basis. Let's look at a temperate region, right? Like would be a swath around the Carolinas, for example, that mid part of the United States, where we have grasslands or temperate forest. And assuming that there we have the seasonal changes, the 4 seasons are about even. What do I mean about that? What do I mean by that? That the 4 seasons are even. That we have about 3 months of 3 months of winter, 3 months of spring, 3 months of summer, and 3 months of fall, right? They're about even. And what's the big difference between those 4 seasons? Well, the temperature, right? And associated with the temperature is also going to be rainfall, for example, and then cloud covering, so light exposure, sunlight, these are natural things. And there's going to be a cycle, right? Where there's going to be higher temperature in the summer and lower temperature in the winter. So we can see that that's like a sinoid wave. It's going to be one big variation within each year, where there's going to be part of the year is going to be warmest and another part of the year is going to be coldest. And then transitioning in between. It's not just going to go from very warm to very cold the next day. There's a transition, right? Those 2 transitions, as it's getting warmer, we call that spring, and as it's getting colder, we call it fall, all right? And so those are natural cycles that occur on a yearly basis. That's just on the temperature. You can add other factors, like for example, the rainfall, assuming that there's going to be more rain in the summer and less rain in the winter, then that's going to follow also along the line, so that when you have more temperature, higher temperature, you also have higher amounts of rainfall, higher amount of water. Okay.
Doesn't the lunar cycle play a part into all of this?
Maybe. How so? What is the lunar cycle doing?
Well, it's a shorter day or a shorter night or so on and so forth, doesn't it?
The moon affecting the daylight?
Well, it also affects breeze, the wind.
The moon, not that I know of. So, okay, so what is the lunar cycle? What do we mean by the lunar cycle?
Well, I mean, lunar cycle is where we circle how it affects our daylight and our evenings. I don't know if I'm expressing it.
I don't think so. No. So the lunar cycle is the phases of the moon, right? There's no moon, quarter moon, half moon, three-quarter moon, full moon, just to give some phases, right? We know that that's a 28-day cycle, all right? As the moon rotates around itself and then translates around the Earth. No, it doesn't rotate around itself. It always has the same phase facing us, actually, right? But it does translate around the Earth. So, but as far as I know, the lunar cycle affects mostly the ocean because of gravity, but not light, because so remember, the moon is an opaque body. You know, it's not a luminescent body. And so it doesn't really, what we see of the moon, like in a full moon, is the reflection of the sun on the moon. Okay, but daylight is the sun. The source of daylight is the sun. Yeah? For the ocean, yeah, for tides. So the most, where I can think the most influence of the moon would be for nature on Earth, it would be the tides along the shore. You know, so there's high tide and low tide that will have an effect on what is called the intertidal region, the animals and plants that live there, where they're exposed to water or exposed to the air. All right, but not on land as such. The big factor, of course, is sunlight, which will vary again during if we're in a temperate region. There is generally the days are longer when in the summer and shorter in the winter, right? So already you have 3 abiotic factors that have a high impact on producers, right? What are those 3 abiotic factors that have a high impact on producers? Light, exactly. Water and temperature. So the summertime, so which do you think is the high growth season for plants in the temperate region? Exactly, because it's a trifecta, right? You have a combination of warm temperature, which has higher metabolism, speeds up the metabolism. You have more abundant rainfall, all right? So for photosynthesis, and plus there's more daylight exposure. Excuse me. And therefore the summertime is going to be the big growth spurt. In contrast to that, of course, the wintertime is going to be the lowest, to the point that the trees actually go dormant in the temperate region, right, with snowfall, and so they literally lose all their leaves, and that's why the fall is called the fall. I mean, technically it's autumn, but we call it the fall because the leaves drop off, all right? And so the trees are dormant. They're not dead, even though they look dead, because they're just brown and no leaves, all right? But they're definitely not dead. They've just gone dormant, and the sap is barely moving inside the tree, so metabolism is slowed down to a bare minimum, just to maintain life in a latent way. And then, of course, the spring, everything starts picking up again, slowly but surely, as the temperature rises and there's more humidity, and the days start getting longer and longer, right? So that's a natural cycle. You can see then that plants would naturally follow that cycle on a yearly basis. So that's number one. Number two is that these communities are made up of populations, and these populations are made up of individuals, and these individuals have a lifespan. What do I mean by a lifespan? That they're going to die sooner or later, all right? It may be a few days, a few weeks, a few months, or a few years, depending on the species, on the individual species. Exactly. And they typically do that, right? So that you have, and for shrubs and grasses and so forth, typically they can be classified in annuals or perennials. The annuals, they will die individually on a yearly basis. The perennials can resprout more and more, but eventually that will die too, okay? So my point with all this is that with all this death of plant material in nature, what happens to that plant material? It starts decomposing, it becomes detritus, right? And then the the saprophytes go at it and start breaking it down further into humus, which then mixes into the soil and so forth with the rainfall and the wind and everything else. So basically, it's enriching the soil more and more and more, which allows for a greater variety of plants to come into the area, and especially the larger plants, which are going to be the trees. Because trees, since they have more mass, biomass, have more bulk, they're going to need more nutrition from the soil. So they need soil that is a little richer. And that will happen gradually. It will leave nature alone. That will happen naturally. It's this movement, this progression from the pioneer stage where there was originally barren rock to eventually an entire forest. It may take centuries or millennia, but if we leave nature alone, typically that will happen. As long as what? As long as the climatological conditions are stable. They can be in a dynamic state of flux within a year, for example, like the seasons, all right? But you see that there's a continuity. Year after year, those seasons are repeated. The cycle is repeated, and so different species get used to those cycles and profit from those cycles, so that different plants will grow different times of the year, all right? But there is a natural succession going on from very small and very few to very large and a lot, which is a beautiful thing, really, when you think about it, because nature has this built-in mechanism of populating and eventually establishing what is known as a climax community. All right. Now, a climax community is defined, still looking just at the plant, at the vegetation at the producer level still, all right, just at the base of the pyramid here, is characterized by some main trees, which are going to be the largest trees, physically the largest, tallest, and thickest trees, all right? Those are going to be the dominant species. And there may only be 2 or 3 or 4 dominant species. Very few in variety, but very well established, large and stable, and they will replace each other. So these trees typically have a long lifespan of decades, if not centuries, all right? The extreme, for example, the sequoias in Sequoia National Park in California was just spectacular. I had the privilege of going there a few years ago. There's one up there that is called Colonel Sherman. Oops. Let's see.
In Jamaica, we had this.
Yes.
We had this rebel. It was a rebel culture.
Yeah.
And we have this tree.
It's
an old cotton tree.
Yes, cotton.
Yeah, and it goes back to like 18th century, 19th century.
Yes. So it's about 100.
This old cotton tree, and it said that this is where culture was found.
Oh yes. Oh really? Okay.
Yeah, so
100 years ago.
Yeah.
Wow. Yeah,
so more like 200 now. 18 something.
Oh, 1800s. Yeah. So 200 years. Yeah. Well, that's impressive. But some of these trees, for example, see, these are the giant sequoias. And it is just impressive. But there's one, let's see.
Yeah, one I gave a name to.
Yes. Yes.
Sequoia Sherman tree.
Yes, this is in Sequoia National Park, and this thing is so large that to see it, you try to back away from it, right? To try to see the whole tree, you have to be so far back that you fall back on your head. it's so big, and this is estimated to be 2,000 years old. 2,000 years old. The Colonel Sherman. This is part of Sequoia National Park. Yeah, it's just spectacular, amazing, and it's a type of conifer, right? Sequoia conifer. But this guy is actually young. It's still living. It's 2,000 years old, still living, but it's considered young actually because they found a trunk that had fallen in the forest in Sequoia National Park. Let's see, Sequoia National Park here.
Stefani, we should complain that we're 70 years old.
We're babes, very, very tiny babes. Yes, yes, it's just amazing. Well, what I want to say is this Sequoia National Park, they discovered a tree, a trunk that had fallen. All right, and this the park as a whole. It is really beautiful. And they did, yeah, it's in California, the West Coast, the real West Coast of the US, all right, the Pacific Coast has spectacular national parks. And what I want to say is that they found a tree there, the trunk, all right, fallen, and they measured the years by tree rings. Yeah. They did coring and measured the tree rings, and they counted from the core out to the crust. They counted 4,000 rings, so 4,000 years old. Okay, dead now, they've fallen, but 4,000 years old by the time he died.
Sherman, you said a baby.
It's a baby, right? It's just it's a teenager, just getting, it's a young adult, 2,000 years old. So it's really not known what is the age limit for these sequoias, all right? But they last so much, so long. It's just amazing. Anyway, that's an example of the other extreme, whereas mosses and lichens can last maybe a year in a cycle, and many of the herbs or shrubs do that too, you know, they're annuals. Other trees, when you have a climax community, are long living. And that's the example that we have here at St. Thomas. Actually, our forest is a climax community of Dade County / pine, right? So, well, okay, before we go into that, then just a recap. We start with the pioneer species, which are typically few and hardy and can tolerate harsh environments. And as the detritus grows and the soil is enriched, as long as the climate continues, then you get the intermediate succession species coming in, shrubs getting small and getting larger into young trees, and then those trees become more mature until finally you have that climax community or the climax forest, where you have a few trees that are the dominant species, and they are obviously the largest ones there, okay? And the whole predicate of this is that the climate is stable. The climate is stable, even though seasonally it may fluctuate, but that fluctuation is a seasonal variation within a particular range, and the range is stable. All right, so people get the picture. And as the Earth, you can think we back out to ecosystems, and what's above ecosystems, a number of ecosystems coming together, what do we have? We have the biomes, right, which are large geographic regions of Earth, the biomes. So biomes, if you think about it, the Earth is rotating and it's maintaining, well, the rotation of the Earth is about the same every 24 hours and so forth. The translation of the Earth around the sun, 365 days approximately. So those two things are stable for really millions and millions of years. So from the big picture perspective, the Earth itself is fairly stable as far as source of sunlight. And then that is going to have an effect on heat. And also the heat will have an effect on the water cycle and so forth. So the three main factors, light, water, and heat, which are the three main factors, climatological factors for growth of plants, are fairly stable on Earth, unless there are some drastic phenomena that will happen, all right, on Earth. Like, for example, it could be heavy volcanic activity or something like that that can change the climate drastically. All right, so we get to this climax community, which is a stable environment. And if you add in, what do we need to add into this, which is not seen in these pictures or caricatures, the other living organisms that are also going to come in gradually together with the plants. What's going to migrate into this area that used to be just rock. Exactly, so the animals in general, all right? Which will be first, will be what? Herbivores. I want you to think in categories, right? And then you fill in the categories of the individual animals that you like. But first, we're going to be herbivores are following the producers. And then come the omnivores, right? That can eat some herbs and can eat some insects or some animals, some herbivores. And then finally, the last to come in to an area are going to be the carnivores. There are fewer in number, they're larger in size, and they typically require a larger range for living. All right, so you can see it kind of follows also the same succession as plants do, only that animals are going to be more motile for sure. They can move around, and there's going to be more interaction of populations coming in and out of an area. But eventually that will also stabilize, so that as these different successions are going on onto the climax community, you also have pioneer animals that are going to come in, like insects and so forth, feeding on the shrubs, and then the others that are following, little mice or whatever, that are feeding on those insects, or even carnivore insects that feed on each other and so forth. And you'll get a population of the large carnivores, for example, in that temperate forest. What are some of the large carnivores? What are some of the top carnivores in the temperate forest? You have bear, you have wolf, you have mountain lion or bobcat or raccoons, yeah, but raccoons, I think they are omnivores. In other words, they're scavengers, so they can eat either animals or plants, whatever they get a hold of, right? I don't know. I really don't know if raccoons are actually carnivores. I think they're omnivores and scavengers.
Well, they eat everything. So.
They eat everything inside, but they can also get eaten by other things, including, don't forget, the eagles and the large birds of prey. All right, they're also top carnivores. And so the top carnivores tend to be larger in size, but fewer in number. And so the populations, for it to be a stable population, they need a larger range. They need a bigger range, right? To have enough food available. Again, keep in mind the biomass, the 10-to-1 ratio as we go up the levels. All right, so I want to bring it home for a moment, since we are familiar with St. Thomas University. I mean, we drive by this place often, and here is a map, a photograph, a Google map of St. Thomas University. It's actually an aerial, a satellite photograph, right? And so to ubicar, to place ourselves, locate ourselves. This is the front entrance, the gate here. This is 37th Avenue. The little road as we meander around. Here is the actual forest that I'm talking about, which is significant for the entire area of campus. We continue along that road. Here will be the chapel, and veer left and veer right. And this is the science building here, parking lot, right? So you can see that, and then this is 32nd Avenue on the other end of campus, the east end. To the north is the Palmetto Expressway up here. And then way to the south is actually the boundary with the high school, Pace High School over here on the east side, and then the Marion Center on the west side down here, okay? So this is the big picture of the campus. As you can see, it's more or less like a square, and a significant portion of campus is this forest that is concentrated here on the northern half of the campus, and it is Day County / pine, Day County / pine, which is definitely a dominant species of a climax community. Way back, most of the peninsula of Florida was covered by Dade County by slash pine. All right, which is, as you know, being a pine is a conifer, meaning that is a tree that is adapted to the northern climates. They have needles instead of leaves. They have cones instead of flowers, and they have internally they have sap. They have resin instead of sap. All right, and so those are three major adaptations to the northern climate, especially during the wintertime when there's very cold climate, and then the snow can break off leaves and so forth, but the needle doesn't accumulate that much leaf. So long and short is that conifers have adapted to stay green year round, and that gives them an edge because even in the wintertime they can still grow a little bit and maintain their vitality. So these, sorry? Right, exactly. So sap, it slows down because sap has a high water content, and therefore in the wintertime, the sap really slows down, barely flows inside a tree. I don't know, it may be that it has to flow a little bit because the tree internally is alive, okay, but it's dormant. Whereas resin has very little water content, and therefore it doesn't really freeze, and it will continue to flow slowly but surely even in the wintertime. It's less affected by the temperature. So those are three major adaptations, which allows the conifers, the pine trees, to continue living actively during the wintertime. Okay. But here we have a subtropical environment for which none of these adaptations are necessary. And so it's quite remarkable that these pine trees have adapted to living in South Florida in the climate, and they thrive. They do very well here, as you can see, so much so that they have become the dominant species of South Florida originally before civilization got here. So as recent as maybe 100 to 120 years ago, the highland of the peninsula, the high areas of the peninsula, which we're talking, I mean, a highland in South Florida is maybe 6 or 7 feet above sea level, okay? It's very flat. It was all covered by these pine trees, natural pine tree forest.
Because the ones that are built with that same part of pine you're talking, they don't rot.
Exactly.
Same resin inside.
That's exactly what I was going to get into. Yeah. Is that these are very well adapted, and of course they don't rot, and because the insects cannot get into them, all right, because they're resistant to many of the local insects that are here that or bugs that get into trees and termites and so forth, and therefore they're resistant to all that, and they make good construction material. And before there was any building code, all right, when this was just being colonized, which was at the end of the 1800s, the beginning of the 1900s, think of Henry Flagler bringing the railroad down and all that, but even before that, when early colonizers were getting here, and this was just the previous people here were the native Indians, which were technically in a prehistoric state because they didn't even have writing, reading or writing that we know of, all right? So they were living in an oral tradition, very primitively, didn't even cut down these trees because they didn't have even metals. They were living in the Stone Age, literally. And what kind of stone did they have? Well, calcareous stone, the local stone, is just limestone, which is not good for making sharp tools or anything like that. Their tools were actually a conch or shells, which were more sharp, but not strong enough to cut down a tree. So the trees were basically left alone until the early colonizers got here. But early colonizers just means a century, a little over a century ago, the late 1800s, all right? And when they found these trees, these are ideal for log cabins and for building their towns. And just in place as they started felling and logging these trees and building their towns. The whole point about this is to bring it to the current state is in a little over 100 years, the pines, these Dade County slash pine, are down to less than 1% of the whole county. Whereas they used to be maybe 8 or 9% of the county, now they're down to 1%, or less than 1%. Basically, almost liquidated, just because they were used for construction and also for burning material, for wood, for the fireplace, for cooking and all that. Okay, it was just fuel right there available. And so we have one of the few pine forests left in the whole county, right here, and that's why it's being preserved, and it's just there sitting quietly, but it's a real treasure. And it's a lung of what is called an urban forest, surrounded by a residential area and commercial, even an airport nearby and so forth. So this has a lot of natural value for the area, very high natural value. And it is precisely Dade County / pine. I have some research going on in there in the forest for reforestation and so forth. One of the big issues is trying to diminish the number of these invasive species that have populated the area, coming from, that were imported from other parts of the world without any natural enemies. So they're kind of taking over. But anyway, so we have our own climax community of Dade County / pine, and we go by it every time we come in and out of campus, all right? You can see it's a significant, it's about 1/3 of the whole campus when you take up this whole area that is not built and just dedicated to that forest. So it's a significant amount. Now, let's look at how this growth curve happens. Exactly. Up until now, we had been looking at it qualitatively. In other words, the number of species coming in, I mean, the different types of species, how succession was happening from the pioneer species to the various intermediate species until we get to the climax, to the dominant species, right? So we were looking at it qualitatively, different types of species coming in and so forth. Now we're going to look at population growth quantitatively, a little bit quantitatively. So again, trying to be in sync with the other course on statistics, trying to get some numbers or thinking in terms of quantities. This is known as a population growth curve. This is a standard population growth curve shape, right? The shape of the curve, the behavior of the curve in the vast majority of populations, of natural populations on Earth. Whether we're talking about something as small as bacteria or as large as a sequoia, all right? All species that we have observed so far follow this normal population growth. And so it's known as a population growth curve, also known as a sigmoid curve. I'll show you that in a minute. But there are three main phases of the curve. If we plot it with two variables, an independent variable and a dependent variable. All right. So again, I'm going through this a little bit in more detail so that maybe some of these concepts will help you in the group projects that you're doing. All right. So we're going to have the independent variable or on the X or the Y axis. Independent variable, typically, which is the independent variable of these two? We have time or we have number of individuals. Time is independent. It doesn't, time is going on whether there's 1 million people in this room or no people in this room, right? So time is an independent variable, and that's typically put on the X-axis, the horizontal axis, all right? So the other variable is going to go in the Y-axis. So we say that the number of individuals will vary with the passage of time. So time will be a constant, whether it's measured in seconds, in hours, in days, in years, millennia, okay? But it's a constant. You're going to have ticks here of the same dimension between ticks. It's just the passage of time, whatever scale one is using. Follow? Yes? Okay. Number of individuals, again, you're going to have ticks going up vertically from 0 to whatever maximum you need, depending on the population, but this is going to be just numbers, 1, 2, 3, 4, 5, etc. It's a linear progression, right? You understand linear progression, 1, 2, 3, 4, 5, etc. All right. So number of individuals of any species within a population, within a given population. This is the typical growth curve as these individuals, as this population goes into an environment and starts colonizing that environment. Of course, the very origin is going to be 0, 0, and then 1 individual, 2 individuals, 4, 8, 16, 32. What kind of a progression is that? Geometric, exactly. When we double the population, right? When we double it, it's going to be geometric. It's not linear, like 1, 2, 3, 4, 5, but it's going to be a geometric progression. All right. And so at first, it's a slow progress. It's a slow progress. Also, keep in mind that this is a dynamic state. It's not just doubling the numbers, but some of those doubled numbers are going to start dying off. Okay, so the net is never going to be maximum. It's going to be a little less than the ideal number. And so the first part of that curve is called the lag phase, L-A-G, lag, because it goes slowly. It lags, okay? It's going slowly, L-A-G, the lag phase. At some point, because the population is doubling, every generation is doubling, right? Then it's going to pick up speed. It's going to pick up speed, not in time. The time is the same time that is passing by, but it's going to pick up, the number of individuals are going to increase exponentially because it's doubling every time. And so it goes from a lag phase into what is known as a log phase. Log is actually short for logarithmic, which is an exponential, all right? And so it's the population is doubling every time here. So the numbers are increasing from now 1 million, 2 million, 4 million, 8 million, and so forth, okay? So the log phase increases the numbers very fast. In a short period of time, the number of individuals increases very fast. Now, do you think that that log phase can be maintained indefinitely?
No, because they all die out. Everything dies.
What's going to happen? Yes, but why? Okay, so yes, the individuals do die, and you're pointing to what is known as the lifespan of the individuals in that species. Every species has a lifespan, right? What's the lifespan for humans approximately? That about 80, more or less, about 80. It's interesting because there's a little verse in the Bible, right? 80 years, an average of 80 or 70 or 80 for those who are strong, it says, right? And in 2,000 years or 4,000 years, I don't know when that verse was written, but we're about the same still. So I think our organs, our vital organs basically last that long, and then they start breaking down systemically, right? So every species has a life expectancy.
And a life producing expectancy.
Oh yeah, well within that there's a reproductive age,
Yes.
right? Which that's what is defined as maturity, biologically speaking, is reproductive maturity. Now, but it's not only the individuals who are dying, because those individuals who are dying are being replaced by the numbers by the individuals who are being born, okay? But there's another factor here. And other factors are typically going to be the environmental factors of that there is the limited resources. You see, they're going to be limited resources, so that's going to start. There's only so many individuals can be fed. There are only so many mice that can feed in this field of wheat, and then there are only so many owls that can feed on the number of mice that are there, and so forth. So everything starts hitting maximum because of limited environmental conditions, all right, or resources in general, limited resources for living. So that's going to start slowing down the population growth, the net population growth, all right? And so it goes into what is known as a stationary phase. The third one, stationary phase. So now, instead of having a geometric progression, you're having a geometric regression until it stabilizes. And this overall shape is known as a S shape, right? If you take an S and you pull it by the two ends, you see has a kind of an S shape, all right, or sigmoid curve. So here in the next slide, I put a little more data. So this kind of curve is known as a sigmoid or S-shaped curve, because sigmoid is the Greek word for that letter that looks like this, right? And when it stabilizes here, that number of individuals, that specific number of individuals here, all right, for that particular geographic region, for that population, that is called the carrying capacity. The carrying capacity. The carrying capacity is the maximum number of individuals in any population that the particular environment can hold. The particular environment where the population is living. Okay, so again, it's the maximum number of individuals that can be sustained in that particular environment for each population. Each population meaning for each species. All right, that's the carrying capacity. And so scientists are always studying what is the carrying capacity of wheat, for example, in a field, and depending on the acreage, right? And then what is the carrying capacity of mice that feed on that wheat, you know, for that particular field, and so on and so forth. And it's always going to be due to the limited resources that there are realistically, because resources are not unlimited, right? Okay. Now, let's look at some examples in nature, briefly. Again, beginning with producers. If you look at this photograph here, the first photograph, you see that there's a patch of grasses here that is delimited, at least from what we can see on this side, by some buildings and maybe a road here and so forth. So this is a particular geographical area, local area, all right, that I can tell at least 2 or 3 different types of grasses growing. There's this thick blade grass over here, right? Then there's a taller one here that seems to be a different species. And then in the background here, maybe a more fuzzy one. So probably 3 or 4 that we can tell just from the eye. I'm sure there are many more, but there could be about 3 or 4 different populations of grasses growing in the same area. By the way, this is another opportunity to point out the competitive exclusion principle that we talked about a long time ago, is that you have different species of grasses growing in the same geographical region, in the same area, all right? What does it tell you about the types of nutrients that they're absorbing from the ground? They're not competing for the same types of nutrients, all right? Otherwise, they wouldn't be able to coexist in the same area. Eventually, one species will thrive and take over the other species. So when you have several grasses growing in the wild in a particular area, next to each other year after year after year, and in a kind of a stable way, all right? So you have different populations of grasses growing in the same area. It means that they're just absorbing different, somewhat different nutrients, are not competing for the same type of nutrients. They're competing for the same amount of light, but there's plenty of light generally in an open area, all right? And they will be competing for the same amount of water, basically, but the nutrients will be different. Otherwise, they wouldn't be able to survive next to each other. Hmm?
Yes.
Yes.
Because they're the ones, all the ones drawn over the sunlight.
Yes, and that could be an example of succession, as those older grasses, maybe they were the ones who got established first, all right, but then as they kind of it was almost suicidal, if you will, for that particular population, because those grasses were successful at colonizing this area, but then eventually they start developing as they die, as individual blades of grass die and so forth, they start accumulating more soil. And then other grasses can come in and can grow faster or taller and drown them out. And so the older population of grass is going to die out and a new population has come in. You just described a succession period. Yeah. All right. And so that will happen in nature. Absolutely. So here's one example. It's just on the producer level with the grasses, right? And there will be a carrying capacity for each one of these populations, each one of these species, all right? Okay, then if you add a next layer, let's say a layer of herbivores, well, let's say these cows on the patch, on the range, right? There's a maximum number of cows that this grass range will hold, right? And so that would be the carrying capacity of those cows. And it may vary also by species, different types of cows, etc. But of the one species, there will be, for each species of cow, there will be a carrying capacity, will be a maximum number of individual cows that can live in that range, in that patch of grass.
And also the farmers actually put them out.
Yeah.
X amount of time in one patch.
Right.
Eat that grass.
Exactly. And then they'll move into another area and allow that previous patch to rejuvenate. Yeah. Exactly. Yeah. So this is kind of an intuitive thing, and that's the carrying capacity. If we go all the way to the other end to top carnivores, for example, here are two mountain lions. Don't miss the second one that's lying down here. Okay. Two mountain lions. And as we can see from the background, they could be maybe in the Grand Canyon area, inside some kind of a cave here. What kind of range do you think they have? Exactly. They have a wide range because remember, they need that biomass of 10 to 1 of previous animals that themselves need a 10 to 1 and a 10 to 1 and a 10 to 1. So if these are top carnivores, then there may be at least 3 or 4 levels below them that will increase 10 to 1 each time. So by the time you get to the very bottom, it's 1,000 to 1. All right. And so they need a very large range for this, let's say that this mating couple of pumas or mountain lion, they need a fairly large range. So that in the range, only this pair of mountain lions will survive. And there may be another pair of mountain lions somewhere on the other side of the canyon here. And they have their own range, which would be more or less equivalent in size, but fairly large, you see? So you can go all the way from this crowded, huge number of individuals, the carrying capacity of grass here in this relatively small patch of land, compared to what's the carrying capacity of the puma or the mountain lion in this, it could be several hundred kilometers, square kilometers of the Grand Canyon. What's the carrying capacity of puma in that square kilometer?
But they're going to be low in numbers.
Yeah, 2.
Yeah.
2. Okay, and if they have pups, then it's going to be 3 or 4, and that's the maximum. And then when those pups grow, believe me, they're going to have to exit and get their own range. All right, because the 4 will not be able to survive in the same range as adults. All right, so you see how it works. When you get up the pyramid, the carrying capacity becomes very low in number, but extensive range. All right.
But that's also we do a nature limits. Population growth.
Exactly. Yeah. So in nature, really, the big picture in nature is that there is a stability.
Yeah.
When you get all the way up to what are the largest geographical areas that we have in nature? what do we call them? About a dozen of them, 9 to 12 throughout the earth. The biomes, remember the biomes? Okay. They are stable in the natural environment. They are fairly stable over a long period of time because they have climax communities within each one of those communities, there will be the carrying capacity of each population is at its maximum. Okay, so I put here the level of ecosystem. Why? Because we want to include also the non-biotic factors, right? The non-biotic factors which makes a community become an ecosystem. Remember, community is just the animals and plants, the living organisms. When we add the abiotic factors, then we have the ecosystem. All right, so this is on the largest side when we have the top carnivores, going all the way to the opposite end to small, microscopic, right? This is an actual photograph. This is an electron micrograph of bacteria growing on the tip of a pin. So this is actually the tip of a pin, all right? The silver part is the metal. This is the tip of a pin, pretty blunt, because this is an electron micrograph, which is several thousand magnitude amplification, and it's been colorized also. This typically are shades of gray, but they're colorized just to show. So you see the bacteria growth here, all right? You can see the individual. This is one population of bacteria growing on the tip of this pin. And they will have a carrying capacity also. In other words, when the tip of the pin gets covered with bacteria, that's it. You know, some bacteria have to die for new ones to take over that space. Okay, so this happens from the very large areas of thousands of square kilometers to microscopic spaces, regardless, wherever there is life on Earth. Okay? And there's a balance there. Each one of these animals and plants have their own carrying capacity. Each species has its own carrying capacity. Okay, so now when we jump to the human population, we can ask the question, what is the carrying capacity of the human population on Earth? Okay, what is the maximum? In other words, reframing that question is, what is the maximum number of people that the Earth can hold? That the biosphere that we call Earth can hold, right? Which is going to be mostly on land because we're not equipped naturally to live in water or underwater. So it's going to be the land mass, right? So that already restricts it to about 1/4 of the surface of the Earth, because 3/4 is ocean. Okay, so let me leave it with that question for a moment. Let's take a quick break, and then we'll come back. And from here forward, we're going to be focusing on human population growth, and human population density, and our footprint on the biosphere, right? Of where to live and how to live and so forth. So I'll take a few minutes break here. Let's see. I'm gonna pause the recording. Okay, so we're back on now. And up until now, we have been looking in this lecture at the succession. We're looking at natural populations, how to go from a pioneer species pioneer species through succession up to a climax community when we have dominant species. And that happens in nature all the time. And so qualitatively, populations of different species will come into an area and colonize it. Over a long period of time, will become established. Quantitatively will be a growth curve for each one of these species, each one of these populations. And that growth curve, the typical growth curve, is a sigmoid curve. Okay. And once it stabilizes, that is the climax community, and each species will have a number of individuals, right? And that is called the carrying capacity. One thing I want to point out, that you notice that the carrying capacity can change for the same species in a different environment. One environment may have more resources than another, all right? So the same species could be more abundant in an environment that has more resources than in an environment that has less resources. So again, think about this, the same species could have a different carrying capacity in different environments depending on the resources that are available. And so really, we talk about the carrying capacity of an ecosystem or the carrying capacity of a region for all the different species that are there. All right, so now we want to look at the carrying capacity of Earth for the human species, right? Because again, this being bioethics is all about our impact on nature and how to live here peaceably with the rest of nature. This is just a map that shows human population density on the land masses, obviously, because we don't have a significant number of people living in the oceans. And you can see that there are three main regions of high density, just globally. The darker red or violet is the higher population density, where this violet is the highest, over 500 people per square kilometer. Basically, it's a scale here, okay? People per square kilometer. You can see the three main regions geographically of the Earth, of the biosphere, is going to be Europe, which is more spread out, then India, and then China. Okay, they're all in the northern hemisphere, and these are the three main areas of the world with the highest population density at the global level, looking at the big picture. Again, Europe in general, even though it's more spread out, including Eastern Europe, and then India, and the Himalayas will be here, the limiting, including Pakistan, and then China. All right. Now, yep.
There's specific reason when you look at that Roman map,
Mm-hmm.
it seems to be less population in that.
Mm-hmm. Right. Well, that is a phenomenon that happens mostly in the Americas, North and South America. In general, the coastal regions are more densely populated, whether it's the West Coast or the East Coast. All right. And a further, because it's certainly not the case in Europe or India or China, right? It's also along the coast for sure.
Well, China's complete, the whole coast is populated.
Yes, sure.
So
and so is India.
No choice,
And so is Europe. Right, exactly. But so it's a good point, because what is a natural limit? And then further, if we look at just the Americas for now, that you say that the center tends to be less populated, obviously, than the coastlands, right? And then a further observation, just from this map, is of the two coastlands, whether it's Atlantic or Pacific, which seems to be more densely or more restricted.
Or restricted or Pacific.
More restricted is the Pacific, yes. In the Atlantic, it's more diffuse, right? Look at how it goes all the way into the mid states here, and even down in South America, Brazil and Argentina and Uruguay, so forth, also are more spread out. Whereas in the Pacific, it's a narrow band. It's a narrow band, all right? Narrow strip, heavily populated, but a fairly narrow strip. And what do you think? What's your intuition? What do they have on the West Coast that we don't have on the East Coast? By way of natural barriers that would contain this population along the coastline. What goes up very fast on the Pacific side, let's say we're in California or Oregon or even Washington, and we're on the coast, right on the Pacific coast, and we start moving inland, what's going to happen? We're going to start going up, right, very fast into what? Into the Rocky Mountains, exactly. Rocky Mountains, which are snow-capped mountains. It's the mountain range. That is, and that is called precisely, that's called the Pacific Corridor. All right. That is called the Pacific Corridor. And from time immemorial, from the migration of, so the general migration has been established to be from Asia across Siberia and across the Bering Straits into what is today Alaska, the Alaskan Peninsula, and then down that corridor, because the Rocky Mountains, remember, begin in the Alaska range all the way down. So that kind of restricts the range of motion for the people, for early people, primitive people, as they were coming down the coast, all the way down into South America and Tierra del Fuego in southern Chile here, okay? So in the Northern Hemisphere, it is mostly the Rocky Mountains, and as they go into Mexico, it's called the Sierra Madre Occidental, the western mountain range for Mexico. And then into Central America, it disappears into Central America, goes actually into the ocean and disappears. Then you have the Panama, the Isthmus of Panama, which is pretty flat sea level. And then it picks up again in the Southern Hemisphere with what range? The mountain range in Southern America, which is kind of an S shape also, is the Andes, right? The Andes, which also have mountaintop, have snow-capped mountains. So it's a very narrow area that is called the Pacific Corridor, and that all has been populated for centuries. Okay, but anyway, so let's look at where people are living, and the big question is, where I left it before the break, what is the carrying capacity of Earth? What is the carrying capacity of Earth for the human population? Because we know that each biome, which is subdivided into ecosystems throughout the world, has a carrying capacity for each species, for each population that lives in that area. And over a period of time, that becomes stable, right? So there's a succession going until that we reach that climax community, and it stabilizes there with a dynamic equilibrium. So the older individuals are dying and the new ones are being born and so forth. And so there's a dynamic equilibrium, but it's stable. How about the human population? Well, we can start by looking at human population growth, at the growth curve, and then figuring out the density, the population density of the world. So let's go there. First, we look at the human growth curve. And this is the growth curve of the human population in the past 2 to 5 million years, going back. Okay, now if we go back quite a bit, these are estimates from a number of sources, but we can say that it starts very, very small. Remember phylogenetics, how we did the phylogenetics, the origin of the human species, all right? It's natural to assume, logical to assume that we started as few individuals on Earth, and in fact, we see some of that from the fossil record, the scant fossil record, plus the other archaeological findings that have been discovered, remnants of cooking fire and remnants of some structures, maybe inside caves and some painting and so forth, the very primitive stuff. Very, very small number of populations of clans, of human clans. If we go all the way back to what is estimated to be the origin of the human species or the human genus, Homo, right? We go to what continent of the 5 continents? We go to Africa and equatorial Africa somewhere within this region here. Here's the equator. So somewhere equatorial Africa is believed to have started the genus Homo. And then we went through all the different transitions, Homo habilis, Homo faber, Homo neanderthalis, Homo erectus, etc. All right. And there has been that gradual but sure migration that we talked about earlier out of Africa, several waves going along the coastline into Asia, going along land up into Europe, and as that migration continued up the coast on Asia, eventually into the Americas and so forth, that expansion of population. But population, we see that the human species has gradually but surely expanded from a focal point throughout all continents today, right? Okay, so that's as far as geography. What about the numbers? What about the population growth curve? Well, this is pretty much what it looks like. A very slow beginning for thousands of years, thousands and thousands, hundreds of thousands of years. Very, very slow. What do we call this phase of the curve? The lag phase, right? Very, very slow. What do you think is the main factor keeping this lag phase so long? So long in time. Here is the independent variable, right? What's the independent variable?
Time.
Passage of time, inexorably, passage of time. These are ticks of 1,000 in general, all right? These are ticks of 1,000. And at this point, it goes into the millions, still very, very flat horizontally. Okay. What do you think has changed? Do you think that the climate of the Earth has changed significantly over thousands of years? Somewhat. We had the glaciations, but that's more in that's in hundreds of thousands of years. Okay, so that has been one effect, the climate change that has gone on with the cycles that we know of. But the main factor here was been generally a high rate of mortality, all right, of infant mortality and overall mortality. I mean, most women died when? The average age of women was in the 50s, you know, until the C-section was invented, the cesarean section. And so most women died in the last childbirth, which also made a predicament for that last child. How's that last child going to be nourished? Maybe for some other woman in the clan. We have to think in the primitive clans of humans interacting, right, with each other. But there was a high rate of mortality for humans for millennia. First of all, we're also easy targets for whom? We're easy target for top carnivores. Pretty much until we were able to harness fire and use fire as a protection, and then develop also weapons to protect ourselves. And so gradually there's an increase, and that turnaround, if you will, from the lag to the log phase happened in the first 1,000 years after Christ, approximately. All right, after the time of Christ. So the first 1,000 years, the first millennium AD, is a turnaround from the lag phase to the log phase, meaning that in general, in those first 1,000 years after Christ, we became much more civilized by way of protecting the population as a whole, okay, with more sophisticated weaponry, also going into the use of the heavy use of metals, right? Making that transition and being able to build cities actually, and construction, civilization as we call it, right? And in the second millennium, from 1,000 to 2,000, full-blown into what is known as the log phase. So he has gone mostly from a horizontal line to a vertical line in the big picture. You see, like it's like an inverted L. Okay. So literally for millions of years, we had a very low replacement level, very low growth rate. And in the past 1,000 years, a very fast growth rate, very, very fast. So we have become extremely efficient. What can we say from this curve? That we have become extremely efficient at surviving. Excuse me. and actually thriving on, on Earth, on planet Earth, on the biosphere. Okay, and thus these numbers here, the reason for these this population. So now we are in a log phase, which means that essentially the world's population is doubling practically. It's not quite every generation because there's still a lot of infant mortality going on and other factors that limit the population. Of course, in general, this is a very general statement. In general, the southern hemisphere limiting factors is going to be ill health and high infant mortality in general. In the northern hemisphere is very, very different. In the northern hemisphere in general, especially the northwestern hemisphere, meaning Europe and North America, is going to be contraception and sterilization, right? That just couples are not having children anymore. So for different reasons, but in general, the population is still in a log phase, growing very rapidly to the tune that we're now about 7.5 billion people on Earth. Okay. This is a projection to 2025. It's anybody's guess, really, but we should go beyond 8 billion people by 2025, which is only about 7 years away, right? All right, this is just by the numbers of the population growth curves of humans, counting the numbers. And then you see that there's some tapering off here. It's anybody's guess when it's going to make that curve into the full sigmoid, right? Anybody's guess, because this could take a long time and continue stretching out, or it could dip quickly, right? The intuition is not going to dip quickly necessarily, but it's going to slowly taper off, very, very gradually. One of the main limiting factors truly is as contraception becomes more and more universal. At any rate, it's anybody's guess what is the carrying capacity. The key question is, what is the carrying capacity of Earth for the human population? We just don't know. Is it going to be 8 million, 16 billion? I'm sorry, this is in the billions, right? 10 to the 9.
You see, Father, there's so many variables to this.
Exactly. There are so many. It's really a very complex question.
It is. I don't think it really can ever be answered.
In one sense, we can say, well, it's kind of it's a theoretical question, but is it that relevant? You know, we can look at something that may be more relevant in a minute.
Unlike other species, man can actually sustain itself to a level, a certain level.
Exactly.
We can plant our food, we can provide, help for ourselves, and we can help ourselves.
Yeah.
The rest of the organisms on Earth can't.
Exactly.
They depend on us.
Exactly. They don't depend on us for sure.
Well, in one sense.
We depend on them.
Yeah.
But they zero depend on us. You think about it, be careful when you make some statements, because certainly the rest of nature does not really depend on us, all right? But we definitely depend on them.
What I mean by that, Father, we can produce as much food as we want.
Yes, we depend on each other, that's for sure.
Yeah.
Okay, so the key question is, what is a sustainable human population on Earth? Which is a very, very complicated question, because like you say, we have artifacts. In other words, no other species, we have to qualify that even, we have to say the vast majority of other species do not grow their own food and do not practice medicine and do not build societies and civilizations like we do, except for in general the social insects like ants and bees and so forth, where they do build up their own colonies, they cultivate their own fungi and so forth underneath the anthills, okay? But not to the level of sophistication that we have, for sure. So I want to look a little bit at population density, the current population density of humans, and project that to start getting a grip on what is the population density of humans on Earth. So here I'm going to do a little bit of Excel. Yeah, let's go in here for a moment and open up this Excel, which I'll also send you at the end of class today. Let's go to this ideal projection. So how do we do a density? Remember, a density is if we're talking about an object, is how thick it is, right? So what is more dense, for example, a pound of lead or a pound of cotton? Which one is more dense? Obviously, that is more dense, right? Lead is more dense. Don't confuse that with weight, okay? So which one weighs more? A pound of lead or a pound of cotton? Which one weighs more? A pound of lead or a pound of cotton? They weigh the same because it's a pound, okay? It's a pound, so don't confuse weight with density. Definitely lead is much more dense than cotton, all right? But pound by pound, they weigh the same. So they just take up, so cotton would take up much more space for a pound than lead would, all right? So we're measuring density here, which is basically, when we're measuring individuals, all right, when we're measuring the density of a population, it's the number of individuals per area, So let's look at the world population. The world population is approximately 7.5 billion. I'm rounding it off to the nearest 100 million here, all right? So 7.5 billion, which is 7,600,000 people on Earth, approximately. And the land area, land because we're going to exclude the surface of the ocean, right? Okay, so land area is about 149 million square kilometers. This is square kilometers, okay? So almost 150 square kilometers, 150 million square kilometers of land on Earth, all right? So if we do the math here, the population density of Earth, the human population density is 51, meaning 51 persons per square kilometers. In other words, we take, what's the math? It's a simple ratio. We take the number of individuals on Earth and we divide it by the number of square kilometers, and that's how we get 51, you see? That's the little ratio here. So this is the average human density on Earth, right? About 51 persons per square kilometer on Earth. If we were to project that to St. Thomas University to see how it looks proportionally, all right, proportionally, this is what I want to do. Let's go back here for a moment. So there's our 51 persons per kilometer square, and I'm calling this theoretic, and you'll see why in a minute. Let's stick with this theoretic number for a moment. Let's project that to size to look at how many people would that be on St. Thomas campus if we were to do now a proportion from that ratio to do it proportionally on our square footage here. All right, so this is that same map that I show you of the St. Thomas campus, right? And these little bars are 100 meters each. Here's a scale, for example. You know, Google Maps is fantastic. It gives you a scale down here. It's probably very small, but the scale is 100 meters, this little horizontal bar, which I replicated here in the green bar. You see the green bar? Okay, that's 100 meters. You follow me? So here's the green bar, so that's 100 meters, right? Okay, then I just switched the color so that they can be seen distinctly. So that's 100, red, 200, yellow, 300, blue, 400. Then it repeats again, 5, 6, 7, 8. So STU campus horizontally from east to west is about 800 meters, all right? Just under 1 kilometer. A kilometer would be how many meters? Kilometer. Kilo is 1,000, so 1,000 meters, right? So this is 800, so it's just under a kilometer. 800 meters from east to west. All right. We go north-south. So what am I trying to get here? I'm trying to get the area. I have to multiply the length times height, right? Okay, so going north-south, say we start in the north, here's 100, 2, 3, 4, 5, 6, 7. All right, so it's not quite a square. It's 800 times 700 meters. So we got back to a little Excel here. There is 700 times 700. Convert this to kilometers so that we have the same scale, right? 700 meters is 0.7 kilometers, right? Just under one. And 800 is going to be 0.8 kilometers. So when we do the ratio here is 0.56 kilometers square. In other words, St. Thomas University is about half a kilometer square. You follow? You with me? All right. So about half a kilometer square. Therefore, this 51 persons is per kilometer square, right? If we divide this number into this number, we get the total number, the absolute number of individuals that would fit on St. Thomas property according to this density, to the density of 51 per kilometer square, which was your intuition. If we have about half a kilometer of property, then it's going to be what? About half of this number, right? Well, we have a little bit more than half. We have 0.56, so that 0.6 counts for a little more, so it actually comes to 29. When we do the math, in other words, here on this cell here, I'm taking 51 divided by 0.56, and it gives me 29. This is 29 people at St. Thomas would be equivalent to 51 per kilometer square throughout the whole Earth. In other words, the theoretical population density of humans. And what does that look like? All right, well, it would look more or less like this. So in other words, here we have 51 people throughout the whole world per kilometer square. At St. Thomas, that is equivalent to 29 people in our half kilometer here square. So you see the little red humans, right? So now it's pretty sparsed out, right? Looks a little sparsed out. In other words, this would be the approximate distance between each person. That's more or less what it would look like randomized on the campus. However, I keep saying this is theoretic because, let's go back to the map for a moment. What do you notice from this map? Do you see an even distribution of humans? The distribution of humans is not homogeneous. It's definitely heterogeneous, right? And that's why we have different densities from less than 2 persons per square kilometer to more than 500 persons per square kilometer. That's a big range of population density. So we naturally tend to cluster, in other words, we tend to cluster. All right, so we have to make a couple of adjustments. The first big adjustment that we have to make, and I say big, really big, is because look at the land mass. So you see the white area, right? You see the white area on this picture, right? So the white area is, it represents the oceans, but now look at the land area, which we're saying that the land area is only 1/4 of the world's surface. However, of the land area, you see that there's a light green area, right? And then the population of the light green, but do you see some gray areas? You see this gray area here. Look at this gray area in the middle of Africa or the Northern Africa, gray area here. Every continent has some gray area. North America, look at the gray area up here, huge. And all of this area in the North Pole, and even what's not shown here would be Antarctica. The whole continent would be gray, all right? What does that mean? That means, and you don't see any population density there, right? So those are essentially uninhabited areas. And why are they uninhabited areas? Generally, they're either too cold or too hot, all right? So the northern swath, the entire northern swath up here, when you take Siberia and you take Alaska and Canada and Greenland and this whole archipelago, that is way too cold. That solid ice up there is not very inhabited. The population density is really, really tiny or none at all. And the same argument would be made for Antarctica way down here. In contrast to that, it could be too hot. For example, the big too hot area is Northern Africa, which is what? The Sahara Desert, the Sahara Desert. And also Australia, look at Australia. Central Australia is a huge, huge desert, basically unpopulated, okay? Then there in the Americas, it's a little different. This gray area in the middle of South America here, that is the Amazon basin, which is basically flooded. It's similar to the Everglades in a sense, even though it's a forest, not a grassland, but it's flooded, all right, periodically, and there's very little, very, very little population density there. And also the Midwest in the US and certainly the Rocky Mountain Range here, very sparsely populated. Okay? So when we look at all these gray areas of land together, without having to do the math, just by the eye, we can say that it's more or less about half, at least half of the world. Again, keep in mind that Antarctica is not even shown here. Okay, so at least half of the world is uninhabited. What do we have to do? So now we have to do some adjustments. It means that instead of being 51 persons, it actually doubles because we only have half the number, half the area, right? We can go to our spreadsheet and adjust these numbers from the ideal to what I'm calling the realistic. So let's look at that. If the actual inhabited land on Earth is not 100%, but only about 50%, half the land, then what happens is we have to cut this land area into half, right? Which is this number here. In other words, we take this number, 149 million, divided by 2, and it gives us this 75 million square kilometers to work with. So that new number adjusted when we use this new number of 75 million divided into the same population, we get the 102 people, which is double 51, okay? And if we adjust STU accordingly, right, it also doubles the number so that what we have is the following. Okay, so instead of being this, it's that. Now this is starting to get a little more dense, right? Yeah. And keep in mind, this is throughout the whole world. Okay, but this is still a homogeneous distribution. In other words, we still have to adjust this further because the whole world doesn't really look like this because this is still a homogeneous distribution. It's just accounting for the inhabited land and not the uninhabited land, which is fair, all right? It's fair. Okay, but this is still not a realistic picture because, again, going to our map, we see that it's not spread homogeneously. We have these large concentrations of population, namely Europe, India, and China. And then also this is Japan, Philippines, for example. This is Korea here, northern China. And so there are other areas that are also high density. This is the, it's probably southern Brazil here, Rio and Sao Paulo, the northeastern coast of the US, etc. Mexico, of course, Mexico City. Anyway, we tend to cluster as humans, tend to cluster into cities that become larger and larger generally. There's a general migration, if you will, that somehow correlates with with education, but not necessarily, all right? That is from rural areas into urban areas. People tend to move naturally from rural areas into urban areas because the thinking is that it's easier to live in the city, but not necessarily, because certainly in the field, out in rural areas, life is more harsh because one has to work land and so forth. Okay, so there's more. It's more labor intensive, if you will, for survival. In urban areas, though, it can be a little tricky because if people who are coming into the urban areas don't have a certain level of education or skills, then they're going to fall into a poverty and misery level, whereby typically these people do not go back into the rural area where they could survive just by their physical labor, and they're going to fall into a cycle of urban misery and degradation, all right? Because there's certainly much more competition. The closer we come together, there's more competition. And one of the big factors for competition is going to be education and or skills, right? So these are some of the complex problems of human dynamics that don't occur the rest of nature because there's that natural balance of a climax community. All right, so we talked about the more realistic number being twice the density, and this is the projection on just our St. Thomas campus, but even this projection is very idealistic in the sense that this implies a homogeneous distribution, which we don't have, obviously, from this map. And so we come to the concept of and the reality of these megalopolies that have been developing in the past decades. All right, there were a couple of decades ago, maybe 3 or 4 decades ago, there were no megalopolies. Megalopolis defined with loosely defined with population density of at least 10 million people or more, at least 10 million people or more. I didn't have time to trace this and do a little, maybe if I have time, I'll do a little graph here on how this has increased, this number. But now there is about 30 megalopolis throughout the world, all right? At least 30 megalopolis. And they used to be, like I say, maybe 30 years ago, 1 or 2 or 3. So this number is also growing exponentially. In other words, we have migrations coming into urban areas and increasing the population. For example, this is Tokyo. I should have labeled this. I didn't have time to do that quickly now for a moment. Well, I'll label it before sending it to you, but just verbally. Basically, this is Tokyo, Yokohama, which used to be 2 separate cities, and they have now amalgamated into one huge urban area, one megalopoly. It's got, yeah, Miami and Fort Lauderdale kind of only big time. This is Tokyo, Yokohama. You can see the Mount Fuji here in the background. I think maybe between 30 and 40 million people in this area of very high density. New York City, of course, not going to get behind, about 12 million more or less, all right? I think this is the UN building down here. And then this is, which one was this? These two are in India. One is Bombay. I think this Bombay, which is now called Mumbai. Oh, this one. It could be. Yeah, LA is another megalopoly. Oh, anyway, I'll look at oh no, sorry, this is Beijing. Yes, this is Beijing here in China. Okay, so this is Beijing, China. As you can see, another megalopoly of very, very high density. We start living on top of each other, we can very quickly increase the population density in a square footage, right? So these are the challenges that we have where our population is clustering into these big, huge megacities. And the irony is this: wherever we're going to live on Earth, we're going to leave what is known as a footprint, right? In other words, it takes some actual physical space in which to live. And by the way, you know, we have to be very careful with some environmentalists on the radical side that say that we're just a polluting, horrible population on Earth and we should be get rid of because the rest of nature can do much better without us. Wherever we live, we're going to make an impact. All right. But we can claim that we have a natural right to live. And if we have a natural right to life, we have a natural right to live somewhere physically. The idea is how to try to make the least impact of where we live, because there's also, excuse me, an inverse proportion of biodiversity and human population growth, right? So the more we grow, then the less biodiversity there is, okay? And why is that? Simply, it's mostly because of land usage. It's the biggest impact, the biggest reducer of biodiversity on Earth is taking up natural environments. And what do we take up natural environment? Mostly for what? For agriculture, right? Mostly for agriculture. In other words, we need to cultivate we need to do farming and animal husbandry, which takes up space. And so that takes up space from a natural environment, okay? And, but even so, we have become very efficient with our agriculture and our animal husbandry, mostly by growing grains, which we have been doing for about 7,000 years, more or less, in human history, to the point where I read somewhere that today, you know how much food we actually produce globally? Well, we produce about 4 times more food than is needed to feed the whole world. 4 times more food is amazing. I was flabbergasted by that statistic, but it's true. I should look up the source because it is true that we produce an abundance of grain, mostly cereals, and that is because of what is known as tertiary or quaternary agriculture. In other words, primary agriculture is just planting a seed and waiting for it to grow and then picking the product of that seed. Secondary is to irrigate it somehow, to draw a little canal from a water source over here, a lake or something, and drain some water and feed it and give it some water, right? That's secondary. Tertiary is to use machinery to cultivate that land and increase the yield exponentially, like we do with the combines and all this sophisticated agricultural machinery that is available. And crop rotation, in other words, really science the heck out of it, like it was said in the movie, so that we have a higher yield per square kilometer, per acreage. And so bottom line is we're able to produce 4 times the amount of food to feed the entire world, the 7 billion of us today. However, that's not the whole story. About half of that amount is lost to either rodents or fungi or bacteria that rots in silos and rots in warehouses and stuff like that, okay? So about half of it is lost to nature, back to nature. Nature takes a big chunk out of our food production. Typically rodents, or like I say, or insects, pests, locusts, and all that stuff, all right? So we lose half of that. We still have twice as much. And it doesn't get to the people who need it, mostly because of the human factor of corruption, of course. However, we produce a sufficient amount of food, no question about it, to feed the world today. And so the idea now is to try to reduce somewhat the footprint and to try to use less land, because the more land we use for living, then there's only a limited number of land, amount of land on Earth, okay? We reduce the biodiversity the more we go into the forest, into the grassland, and so forth. So to try to reduce that, and we can do that certainly by increasing the efficiency, in other words, the technology that is used, even with hydroponics and things like that, where food is grown or plants are grown on water or nutrient systems that can be suspended inside warehouses with controlled environment and all that, right? It's used a lot also in animal husbandry for chicken, for pigs, etc. So that's the idea, is using technology and goodwill, and also, but especially goodwill. These are complex factors that are occurring, but we have the capacity. We're the only ones who have the capacity when we look at these issues like this. Now, one of the challenges is precisely that population growth curve, right? Which again, it's anybody's guess what's going to happen going forward, how this is going to react, and if we can reach that carrying capacity before we end up, just contaminating the earth with our waste, like we saw in the previous lectures, and just with using more and more land. But what is a little paradoxical here is when we look at the megalopolis, going back to these two slides with the concentration, with the high density areas, and then what happens, the quality of life or the lifestyle of people in this area, there is also generally there is an increase in crime and violence and lack of healthy living, if you will, overall for people in very high densities. So another question that could be asked, I'm just raising question at this point, is what would be kind of the ideal population density for us to have, on the one hand, a minimal impact of the environment so that we don't take up too much of a footprint, right, horizontally, say. So that requires certain high density. If we don't go horizontal, we have to go vertical. But not so vertical that we become violent and that there will be overall ill health in that city because we just can't get along. We're too clustered, we're too on top of each other, literally. Okay, what is the ideal? What's the balance between those two? It's anybody's guess. It has to do, there's so many, like you pointed out earlier, Louis, there's so many factors involved here. There are human factors, there are environmental factors. Mainly there's, to me, minimally, there's a factor of education, value system, family life, these things that are basic for any society to survive, right? Civil governance and so forth. So all these things are respect for law, all these things factor in big time. Huh? Yes, which is huge, right? Spectacular.
Yeah, this is huge. We adapt to just the whole,
Exactly.
And that represents also our whole market.
Yes. However, we adapt variously, more or less to different types of environments and so forth. When it gets too crowded, then we start reacting negatively. So
Right.
where is the balance, the ideal balance? Okay, and we see these migrations back and forth, people moving out from downtown, moving out into suburbia, and now coming back into gentrifying older cities where people like to live more in the urban setting, trying to use the car less and walk around, have everything available within walking distance. So it's a back and forth thing.
This is the fundamental question of document bank.
Yes, that is one of them, exactly. That is one of the claims there, and how the Pope in that document is trying to challenge us to look for new creative ideas on how to get along with one another, essentially survive and thrive as a human population, as God's image, without killing each other and killing the environment in the process. Okay, so it's challenging. Different areas of the world are seeing it more or less. One common factor about these 4 photographs that I just realized in general is the amount of haze that can be seen, right? This is a clear day. This is one clear day in New York, but if any of you have been to New York, you know that this is not necessarily the standard, okay? It's, these cities all suffer from this issue of smog for decades now. Particles in the atmosphere that are being breathed on a daily basis. Okay, so finally, so I'm just raising questions here. In the next two, we're going to look at energy in the next lecture. So we have two more lectures to go, right? Next lecture, next Saturday, will be on energy and energy alternatives and things like this from fossil fuels. And then the very last one is on the big question of climate change and global warming. So picking up a little bit on the basis that we established today on human population growth, combining these next two lectures into the final lecture, okay? I want to end with the concept of sustainability. So what is sustainable, right? What is a sustainable human population? To me, it's an open question, really. What is a sustainable human population of Earth? We're already at 7.5 billion. That has increased dramatically in the past few decades. And it seems to continue increasing, but we really don't know for how long. So what is really sustainable? Well, the UN tried to go at it. They had a meeting on sustainability in 2000, all right, which over 150 nations participated in that. Of the almost 200 nations, I think it's about 195 nations in the world today. So most nations of the world belong to the UN, from the whole spectrum of governance that you can find. And then there are many also other entities that are called NGOs. You're familiar with NGOs? NGOs are non-governmental organizations. NGOs. I'm looking for the little end. Oh, there we go. What do I need here? Non-governmental organizations. Many of them participate in the UN also. And so in the year 2000, they came up with what they call the Millennium Development Goals, right? Millennium Development Goals, which were 8 at the time. And the goal was by 2015. Yes, right. Now, this doesn't speak of the means that they want to use for obtaining these goals. These are goals or ends, right? But this doesn't talk about the means. I've bracketed the means for now because many of the means that they propose are actually utilitarian, which would be offensive to our value system because it's manipulating people one way or another. But the goals themselves, in principle, are good, honorable. 8 goals originally. I would say definitely ambitious, like eradicating poverty and hunger, all right? Gender equality, well, it depends what you mean by gender and so forth, I know. But these are the goals that in principle would line up with a Judeo-Christian value system as goals themselves. Now, how to achieve them? That is, certainly we can say that child mortality, reducing child mortality is definitely a Judeo-Christian goal, all right? So how to achieve them is the challenge, right? Maternal health for pregnant moms, for sure. That's a laudable goal. How to achieve them is the challenge because they have a particular vision that doesn't necessarily line up with our Judeo-Christian value system. All right, of the means. At any rate, these goals were obviously not obtained by 2015. And so there was a second meeting, and now these goals have been adjusted and augmented, right, to double, more than double, to 17 goals. And they added another 15 years to 2030. So the number keeps increasing, okay? And they are just from these two numbers, that's a geometric progression there, doubling the number. So as goals, certainly they are laudable, if you will, but how to achieve it is the challenge. And I think that, quite frankly, it's not responsible to be, let's say, sarcastic about it, say, well, it's not achievable. It's every person for himself here and see who can fight it out the longest, may the strongest win. No, we are one humanity, and our Holy Father is challenging us to recognize that we are one humanity and we are each other's keeper one way or another. So how to do this in an intelligent way and in a value system whereby it's respectful also of values and not just sterilize massive populations of the world and so on, okay? So I'm just raising questions in this lecture of how to get a grip on what is a sustainable development for the human species. Being that we have much control over our development, unlike other species that when they just get to be too many, they're selected out naturally, right? They're cut down, they're culled down naturally to that stable, through the carrying capacity. But us, no, we have managed even to live, well, we've managed to live in every environment on the Earth to a certain degree, and even we've managed to live in no environment, like in space, outer space. For example, the International Space Station, which is the largest man-made artifact on Earth, is also known as the ISS. This is a multi-nation effort. I've seen images of it, right? That is the International Space Station that has been built little by little. I mean, all of this material, this is floating around in space. All of this material has been built on Earth and shipped up there and assembled by a community of scientists and technicians from different parts of the world, assembling this artifact that I don't know for how long actually has been up there, which, by the way, I understand now is becoming obsolete and will be coming down in a few years, actually, and crashing through the atmosphere and burning up through the atmosphere. But it's a huge, huge space lab and living quarters, and some astronauts have actually lived here for over a year, okay, in space. So talk about a totally artificial environment that we're capable of producing. Of course, this is relatively low density, right? We couldn't fit the 7 billion of us over there. But you see, it's self-sustaining. It generates its own electricity through solar panels and so on and so forth. And there it is. Stuff in this station is recyclable. So we have the capacity, right? The challenges and the opportunities. How we manage to do this is a big, big question of concerted effort. In my mind, it has to be at least certain key factors like education and a certain value system, like the dignity and the sanctity of human life at every stage of development. So we honor every living being on Earth, and also respectful of the environment. But big challenges that we have ahead, right? How we deal with these challenges, well, it's up to us. One issue that the last one, I think has a lot of merit is the partnerships with different groups, individuals, entities, nations, institutions, etc. Because the more people will get involved in talking about these issues and coming up with possible plans, then overall, the more refined that plan is going to be, right? Everyone has a stake in maintaining the Earth and maintaining our human population on Earth. Not everyone has the same idea of how to do that. Okay, I'm going to end here. Any questions or comments from anyone? No? Let's see who's in the tile. No? I don't think there's anyone here any longer. That's interesting. It just dropped off. I don't know what happened there. There's no one else in the tile. Okay. Anyway, the recording is here, so I'm going to end the recording now, unless anyone has any questions or comments about the different slides. No? I'm going to stop then, and we'll end here. And remember, we only have 2 more lectures the next 2 Saturdays, right? 16 and 23 of June. So for those of you who have still pending summaries, please catch up quickly, because I'm gonna close it at the end of that second Saturday I have to then present the grades and post grades and all that, all right? So please catch up. And also, while I'm at it, a word on the internship, because since this course is ending shortly, you'll have the rest of the summer to suffer through the statistics course and get that going, right? So that would be the only course you have to suffer through that one. And remember, folks, we always say this in education: no pain, no gain. All right? No pain, no gain. The athletes do that physically. Yeah, we do that intellectually. All right? So it's going to require more of those ATPs. But truly get into that, and don't let that internship lag until the fall semester, because we're going to move quickly into the healthcare course then. So try to get that internship done in the rest of the summer that you have. All right. If you have any questions or comments about anything, you can email me, and we'll go from there. Thanks again, and